Okay, okay. So it's my pleasure to share some insight on what we are doing with AI at Imagine Optic, and in particular in wavefront sensing. So we are a small company founded in 1996. We are about 60 employees, and we developed a whole catalog of solution for wavefront sensing and adaptive optics that we are deploying all over the world. So we have more than 2,000 sensors deployed in many different industries, as you can see here at the screen. And innovation and research is really at the uh, heart of our approach for developing all these solutions. And of course, AI is part of our current topic of research. Um, so AI is almost everywhere now, nowadays. And in our case, in optics and within the group, what I will do is to present two implementation we did, and discuss a little bit pros and cons. So first, use um, for us is denoising of images. So here at the screen, you have some images acquired in ophthalmology and microscopy application, and we use AI to remove the noise of these images and make them easier to interpret without affecting the resolution. So as you can see, result is pretty good. We are pretty happy with this application. Um, we also use AI for optical metrology and processing the raw signal we have for in our wavefront sensors. And this is what you can see at the back. We are doing wavefront sensing based on Shack-Hartman approach. So it means our raw signal is consists in a lot of small points on a camera. Okay? So just as a reminder, what we do in our sensors is to embed a microlens array that you can see here from the side. Each microlens is sampling the incoming beam and focusing centroids on a CCD. And by analyzing the lateral position of each of those centroids, we are able to reconstruct the slopes of the wavefront, meaning the direction of propagation of each rays that has been sampled by the microlens. So we get two informations by microlens that allows us to reconstruct some small phase map, and by integration on the pupil of the sensor, we reconstruct a complex map. Some years ago, it has been proposed to maybe do a little bit more with this raw signal by not only analyzing the lateral position of each centroid, but also analyzing the intensity distribution of the centroids. Because as we know, the focal point of a lens is affected by the aberration the beam carries. And you know that if you have astigmatism, for example, the focal point is going to be something like a line. If you have coma, you also have a very easy to recognize pattern on the intensity. So here is the intensity to do more and to apply phase retrieval based on the intensity of each centroid. So we pursued this work and adapted it for the Shack-Hartman wavefront sensing. And basically what we do is now at the scale of a micro lens, we can recreate or we can analyze the distribution of intensity coming from up to 9 different type of aberration. So here on the right, we are able to linearize all the aberration and reconstruct a complex phase at the size of the microlens. So instead of two modes, we have nine coefficient of legendre in this case, and this gives us a lot more resolution. So I'm not gonna show you how we demonstrate the increase in the resolution. But if we have a look to the transfer function of a standard Shackleton wavefront sensor here in gray, and we compare it with the phase retrieval approach, we can see we increase resolution by a factor of 4 in the x-axis and 4 in the y-axis. So it's a total of 16 time increase in resolution. Visually, this is super clear. On the left, you have a faceplate measured in the sphere with a sphere wavefront sensor. And with the same hardware, the phase retrieval gives us this kind of map where we have 112 by 112 phase point. So it's quite amazing, the improvement we have. We deployed these algorithms of phase retrieval in all our catalog of products from sensors up to complete solutions for lab and prod. Now the question is, uh, could we use AI in order to help us in this phase retrieval lift reconstruction? It, it, Saying it in other words, this is exactly the same problematic that my colleague Daniel presented in the first presentation, analyzing the spot to reconstruct the phase, the wavefront, but applied to 680 points by 580 points. Okay, so what we our approach has been to replace the interaction matrix we do on the analysis of each centroid focused by an AI network. So in our case, what we do is we use deep learning, which is a subset of machine learning that presents the advantage of not making easier the preliminary phase of pre-processing and feature extraction that hasn't does not need to be done by a human, so that's an advantage to us. But to work correctly, what you need is a large amount of data to train the network. So the guys at Google, I saw they like to compare this with a rocket. So your deep learning network is a huge motor, and you need a huge amount of fuel in order to power your rocket. No, and if you have a small motor and a lot of fuel, your rocket doesn't go. But the opposite is not good either. So the question for us is really to be able to create this data in order to train the network. So in our case, we went down to the rock signal, again, all our centroids, and we generated an infinity of centroids, each of them corresponding to aleatory phase combination. On top of that, we tried also to add some noise contributions, like the noise from the camera and so on. There are also other contributions that are more complicated to take into account, like, I don't know, coherence of the signal and so on. It can be done better. And from all these centroids, we generated our lift small intensity pictures that we use for the training. So to give you an amount of the magnitude of the data we generated, we created 190,000 images for the training, and we kept 10,000 for the testing. So that's on what we have been training the algorithm. Results are, in terms of accuracy, we are pretty happy with the result. As you can see here, AI approach on deep learning is giving us a better or smaller error on the wavefront than our classic phase retrieval matrix-based approach. So that's pretty good. Also, it behaves very well in terms of dynamic range. So this is the displacement of each centroids. And we can see that the error is maintained pretty well, even for large slope that correspond to surfaces with a bigger deformation than our standard approach, which is here in gray. So at first glance, it seems pretty cool and a pretty good approach. Now, are these two parameters the only one to be taken into account? And here is where I think we have to weigh carefully pros and cons. So accuracy and dynamic range are on the side of the AI approach. Now, what we have seen also is that robustness is not so good in the case of the AI. And by robustness, what I mean is that uh, the algorithm is only good for what it has been trained. And as soon as you introduce something different in the raw signal that the algorithm hasn't been trained for, then it starts giving wrong result very fast and quicker than the matrix approach. Again, this is based on training, and it means that maybe we should train it for other configuration, but we have seen that uh, unexpected event affects a lot. And when I say unexpected event, it might be you have a little bit of dust at some point in your sensor and something like this. No, so um, situation you didn't foresee. In terms of usability for us, uh, processing frequency at the moment is still faster with the phase retrieval based on on our matrix than in the AI approach. Uh, this is largely due to the way it is implemented. And we are very confident that with some effort on the way we implement, and maybe trying some GPU approach and so on, we can speed up the AI. But as we are comparing the new algorithm with one that benefit from many years of development, at the moment, it's still faster by traditional approach. And last, as manufacturer of wavefront sensor, there's another aspect which is very important, which is the the manufacturing time, and in our case, the calibration. We calibrate all our sensors individually in order to make them able to measure at lambda over 100 um, and uh, and in the case of the traditional algorithms, uh, this is a process that is pretty fast. It relies on a couple of measurements. So it means for us it takes minutes to be performed. In the case of the AI approach, um, we have to redo the training of the algorithm for each sensor. And that is because we take into account the signature of the optics that is mounted on our wavefront sensor. So we cannot capitalize on the training that has been done one time. We have to redo it for every sensor. And this is hours and hours of training at the moment. So that's kind of an issue for us at the moment. Okay. So so that's it for me. Yeah. So I presented different application of AI in the different application we deal with at the company, and compared some pros and cons with uh, alternative we have available within our company. And our conclusion is really that benefit of AI depends largely of the application and the constraint, and that moment, working or processing images in live uh, is uh, is still uh, is still an issue for a larger deployment or systematic deployment, let's say, of this kind of algorithm.
Thank you, Rafael. Any question for Rafael? We have time for one question. Yes, Colin, please go ahead.